Welcome to the Nimble American Rescue Plan webinar series. This webinar series highlights the projects funded through the American Rescue Plan. The goal of these projects is to help the nation prevent, prepare for, and respond to coronavirus public health threats. In this webinar, we will hear from Hooman Tafreshi on the project, a new generation of high-efficiency HVAC filters that can be used with existing infrastructure to stop the spread of coronavirus through recirculation of air. You can find additional webinars in the series on our website, www.nimble.org. And now we will turn it over to Hooman.
Thank you very much, Daniel. So this project is funded by NIST through Nimble. People I would like to acknowledge are Matt Russell and Sonny Jones at Nimble, and NIST at NIST, Kelly Rogers, Andrew Persilli, and James Radney. The principal investigator of the project is Dr. Behnam Pudehimi, who is the director of Nonwovens Institute at NC State. And I'm the co-PI of the project, an associate professor in mechanical and aerospace engineering department at NC State, and associate director for research at Nonwovens Institute. So to start with a little bit of background about designing a filter is a device that removes particles from air or from water. A good filter is the one that removes unwanted particles without creating too much pressure drop. And the challenge here is how you can design a filter that has a lower pressure drop, but same collection efficiency, or how you design a filter that has improved collection efficiency, but not at the expense of adding pressure drop. That is a challenge, and is always a trade-off between pressure drop and collection efficiency as you design a new filter. Just to give you a little bit more background about how a fibrous filter filters airborne particles, there are 4 basic mechanisms for capturing particles. One is called initial impaction, where you have large particles or fast particles. They travel in air, and because they cannot turn around the fibers, they get captured due to high inertia. There's also interception mechanism, which is the case where the geometry of the fiber and particle is such that as the particle try to pass around the fiber, is get intercepted by the large size of the particle or comparable size of fiber and particle combined. The case of Brownian diffusion is where you have small particles. They're so small that they're comparable to the mean free path of the air molecules, oxygen and nitrogen, which is about 65 nanometer. In that small scale, the field around the nanoparticle is not a continuum field, and the random collisions between these molecules and particle make the particle move on a zigzag path as it follows the air around the fiber. An electrostatic mechanism, which is a very important mechanism, is the case where you have either the fiber or the particle or both are charged. And Coulomb force, which is the attraction force between charged object, or polarization force, which is the attraction force between a neutral object and a charged object, in this case fiber, come into play to basically attract the particle toward the fiber and remove it from the air. So for this project, we were focused on designing a residential HVAC filter that can capture coronavirus. There's a big debate about the size of the coronavirus. It seems to be between 80 to 150 nanometer in size. What we don't know is that when somebody talks or coughs and droplets comes out of the person's mouth, how many of these viruses are in each droplet, because we know the droplet evaporate and what is left in it is the viruses. And how many viruses, and are they kind of agglomerate into shape of a one large cluster of viruses, or they are individualized? So because of all these unknown, in order to have a filter that can capture coronavirus, we have to have a filter that can capture anything less than a micron that will cover individual viruses or groups of viruses. As you see on the screen, the current filters in residential buildings have a MERV rating of about 8. And MERV rating is an industry standard for rating performance of a filter. In order to capture coronaviruses, we need to go up to MERV 13, which is somewhere what you see here. And these MERV ratings are based on categorizing particles into 3 groups of 0.3 to 1 micron, 1 to 3 micron, and 3 to 10 micron in size. And you can see here in this red color, which group of particles are captured to what percentage by filters of different rating values. So 8 MERV rating doesn't capture any of the submicron particles as you see here, whereas a MERV 13 filter can capture 50% of them. Now, if you are looking to purchase or install the MERV 13 filter, that performance should also be always accompanied by the velocity at which the filter is tested. A typical conventional speed at which the filter is rated is 492 foot per minute as the velocity of the flow in the duct. And this duct, which is based on ASHRAE 52.2 standard, is 2 feet by 2 feet in width. So you're looking at this picture here and shows the dimensions. You typically have a pleated filter, and 24-inch by 24-inch or 2 feet by 2 feet is the size of the filter, the size of the duct. Flow through the duct is 492, again, a conventional speed. And then you can calculate the velocity by which actually air goes through the fabric of the filter, which we call phase velocity. Phase velocity and velocity in the duct have a very simple relationship between the actual area of the filtration filter and the area, projected area of the duct, which is 24 by 24. Now, you can have more pleats or you can have less pleat. Increasing the number of pleats decreases the phase velocity that you see here. And when phase velocity is decreased, then performance of the filter is improved. It means it can capture better. And also the pressure drop of the filter decreases. So increasing pleat count is a very good way of controlling pressure drop and efficiency. The challenge that you will have is that practically you cannot have too many pleats in 1 inch. So pleat crowding or basically the mechanical rigidity of the filter itself is a bottleneck in just simply adding number of pleats, which means you can improve your MERV rating by either making a better fabric for the filter or by making a filter that is more pleatable. Then you can add more number of pleats per inch. Now, the problem statement for us is that MERV 13 filter is needed to capture coronavirus. Most residential buildings do not have an HVAC system that can power a high efficiency filter. The amount of pressure drop is so much high that your unit cannot handle. In addition, when you put a better filter into your HVAC, because it captures more particles, it gets loaded more easily. And it means its pressure drop is going to increase faster. So not only it needs more power to run, it also needs to be changed more frequently. So our goal, as I said, is to produce a MERV 13 filter that can capture particles without adding too much pressure drop to the system. So we targeted 65 Pascal for the MERV 13 filters. The typical MERV 13 filters at the 492 foot per minute velocity, they generate about 75 Pascal. So we targeted 10 Pascal below the standard for the conventional filters. And our approach to solve this problem was basically 2 manufacturing methods accompanied by a computational study. The manufacturing method was based on two technologies, spunbonding or spunbond technology. You see a picture of it. This is a facility at Nonwovens Institute that produces spunbond fabrics. The other technology is the staple carded nonwovens, which are short fibers put together and form a filter. For both of these technologies, we are considering polypropylene and PLA as the two polymers, because these two polymers are very different in their triboelectric performance. Putting these two polymers next to each other can create charge, which is a very important step in creating high efficiency filters. We also do computational work that adds at micro scale, which is fiber level, or macro scale information that we need in designing a filter. So I start with computational part because that also gives the background information we need. So experimentally, we noticed that when we make these charged filters and we load them with particles, basically we test them. Surprisingly, when you load the filter and you normally expect the pores between the fibers get clogged and therefore efficiency go up because now it's more restricted. We notice that efficiency goes down. And this is what you see in this plot where particle capture efficiency is measured for particles of different sizes. And the black circle is the clean media. And you see the performance here. As we continuously loaded the filter with salt particles with different amount, then we noticed that efficiency is actually going down, which is very surprising. So you add all these particles, the pores become smaller, but efficiency also goes down. So we didn't know what's the reason for that, but we came up with a hypothesis. And the hypothesis is that because the media is charged electrostatically and is a bipolar charging, which means fibers have one positive side and a negative side. If you look at this cartoon here, the green halo is the electrostatic field around the bipolar fiber. This is the fiber. These are the particles traveling. Red and blue are particles of different polarity. Some are positively charged, some are negatively charged. This is the nature of aerosol in air. And the negative one are attracted to the positive side, and the positive particles are attracted to the negative side of the fiber. So because particles are charged and fiber is charged, but they're attracted to the opposite side, the overall electrostatic field around the fiber is reduced. As you see, the green halo is getting smaller. That is what we call charge neutralization, is one reason for the performance of the filter degrading. The other one is charge shielding, and that is because when the particles are deposited on the fiber, the air is streamlined or pushed away from the surface of the fiber, as you see here. The dashed line is the original streamline for clean filter, clean fiber. And when these particles deposit, they push the air away from the fiber. And when air is pushed away, particles that are airborne also are pushed away. So they go farther away from the fiber, and they actually fall outside the electrostatic field of the fiber, so they don't get captured. So these two mechanisms, we believe, are the reason for efficiency of an electrostatically charged filter decrease with increasing amount of loading on the filter. We also did a series of micro scale, macro scale, or multi-scale simulation where we have a filter here in this gray area, and we assume this to be a series of tiny little filters combined, and each one of these is a fibrous structure. So instead of having a heavy computational work, we improve the CPU time of the simulation by doing multi-scale simulation. And we actually simulated how, as particles deposit in a filter, electrostatic charge density, which you see plotted here, is decreasing. So you see a lot of red here, and which is the highest electrostatic charge. And as particles are captured with different amounts, as you see with beta shown, electrostatic field is decreased. That's exactly what I was explaining in the previous slide. The charge shielding and charge neutralization lower the amount of electrostatic attraction force in the filter. And here, the bottom picture shows the solid volume fraction of the filter increases due to particle capture. It has like 13% solid volume in it. And as particle deposit in the filter, there's more mass in the filter, or porosity of the filter is reduced. So with that computational tool, we simulated what was experimentally measured. Again, you have particle capture efficiency versus particle diameter. And these different colors are for different amount of loading, which is salt particle in the filter. And circle, the black circle is clean filter experimental data, and the black line is clean filter simulation results, as you see here. And as we loaded the filter, then we noticed the efficiency went down, and simulation and experiment were in good agreement. And also we predicted pressure drop. Experimental data are the circles, and the numerical simulation predictions are is this red line here. Again, good agreement between simulations and experiment. So we built some knowledge to be used in designing the filter. So when it comes to manufacturing of the filter material, as I mentioned, there are two methods we consider. Method one was the spunbonding, which is a continuous filter formation from polymer all the way to the filter. And we have bi-component fibers. They are polypropylene and PLA. As you see here, we added 4% charge stabilizer in the polymer so that as it charge stays in the fabric. The different variety of combination of these percentage of PLA and PP were tested in island in the sea or segmented pie configuration. And the resulting filters were tested in a filter testing machine by Pascals. And some of the results are here. We had variety of different combination of these polymers, so I'm only talking about a few that were the most successful. So polypropylene PLA was at a certain basis weight, and they were hydroentangled together to split the fibers and make the two polymers exposed. They charge by themselves, and charging efficiency or collection efficiency at E1, which is 0.3 to 1 micron particle size, 1 to 3 micron particle size, and 3 to 10 micron particle size. They're all tested. Numbers are here. It categorized as MERV 13 that we were targeting. To ensure the pressure drop meets what we were hoping for, we pleated them in two different ways. With 36 pleat in a 2 feet duct, we could reach 60 Pascal pressure drop, which is less than what we were looking for. So it's very good and successful. The number of pleats are a little bit more than what we expected. But the good thing about the fabric that was made in this trial is that it is so pleatable. It is a little bit more stiff than a conventional filter, that therefore pleating has become more successful. Because of this, so you could pleat more. You can have more pleat count per inch, and thereby you can lower the pressure drop, as I mentioned earlier. It could also be used in a double layer filter to efficiency to go to very high efficiencies, but in that case, pressure drop goes to 104 Pascal. So this is more than what we need, but efficiency for that pressure drop is 99, 98, 79, which is way more than a MERV 13 efficiency. With the second approach, we had, as I said, carded web, which is blend of two different short fibers blended together and then needle punched. These are also segmented pie or bi-component fibers, and different colors show different amount of PP and PLA. And these were blended together. These experiments were also very successful, except that because of the triboelectric charge that built up during mixing of these two fibers, handling of the web is a little bit difficult. So proof of concept is shown, and efficiency is at the expected level. But to scale up this system, we need some machine improvement to avoid fibers basically sticking to the belt or to other part of the machine. Here you see a picture of the mixer where fibers are blended. This is the cross-lapper where the non-woven web is cross-lapped to increase the thickness of the media. And this is the production and the spraying some water to temporarily reduce the electrostatic charge so the handling becomes more successful. So again, this is a proof of concept study. Some additional machinery in this case is needed to make this a commercially feasible process. I would like to again acknowledge NIST and Nimble for providing financial support and a very good collaborative work we had with James Radney at NIST, who helped us with many aspects of this project. We published the result of our work in Journal of Earth Science, and it is available for additional information. With this, I stop for any questions.
Thanks, Hooman. We do have a few questions we wanted to ask. What steps have been taken since the end of the project to license this novel filter technology to manufacturers?
I wish Dr. Purlehini was here because he was more involved with the technology part of the project. I think there are some conversation going on with some companies. I think, I don't know at what level the conversation has advanced, but I think I need to get back on with you on that.
Okay, no problem. In addition to the filter technology, did the team develop any tools and methods of testing that could also further benefit the industry?
Absolutely, yes. I'm glad you mentioned that because in 10-minute presentation, I couldn't talk about all the things we developed. So a lot of things were developed. Some of it were computational, some of it was experimental. So computational part I kind of covered. We basically completely developed we developed a complete new way of simulating electrostatically charged filter when it's loaded with particles. That is new and it's never done before. So from computational part, we have a new tool now. From experimental part, a series of small equipment were built. We built a charging device, a handheld charging device, just to be able to investigate corona charging in different ways. We built a charge measurement device that was also used to characterize corona charging. We built a Faraday cage that is used to measure the net amount of charge in a material, like in a filter. I think we had a few other gadgets we built. So it was a very successful project, in my opinion. We built a lot of things and a lot of knowledge was created. We studied corona charging and tribo charging both. What I presented was only triboelectric charging, but we also did a lot of work on different ways of using corona charging for charging the fabric.
Excellent. And one last question. What next steps would this project team recommend for filter technology development or analysis moving forward?
I think, I wish this project was more than a one-year project because, as I said, we built a very good foundation to move forward. Experimentally, as I mentioned, we have some new way of making filter. There are small problems to be solved. Like, as I mentioned, the web handling is a challenge. Is not something that it cannot be resolved, but it requires some more machine modification. Electrostatic charge, when it creates, basically fibers stick to any surface. So we must be able to kind of lower the amount of charge stored in the fabric during production, but be able to charge it later again. And the technology is available, is not completely reinventing the wheel, but it needs some modification. So we have the background work to move forward. And computationally, as I said, there are many other steps that need to be taken to get to a point that we can say, if I want to build a filter for this building and I'm expecting to operate at this level for this condition, what fibers I use, what thickness I used, what porosity I used, how much I charge it. Do I charge it polarly, unipolarly, or bipolarly? So there are a lot of things need to be done in order to get to a point of engineering filter from a computer all the way to manufacturing. But I think we had a very good start.
Thank you for watching our American Rescue Plan webinar series. To find additional webinars, visit www.nimble.org.